All right, so this is the November meeting. 3 days before the Geminids, which is the big event this month. Welcome. We have 4 people in the room here. We have 2 new members, or 1 member and 1 guest in the room here. We'll get to those introductions after the presentation. As most of all of you hopefully know, our NASA presenter fell ill and is unable to join us. Hopefully we'll be able to reschedule that, but Greg, our frequent presenter, probably need to make a frequent presenter award for Greg. Jumped in and is going to be doing a presentation on OSIRIS-Rex and Hyabusa 2 missions. So I'm going to go ahead and stop sharing and turn it over to Greg.
Okay, thank you, Chris. Okay.
Well, yours, Greg.
Okay. I don't see my. I don't see my
your presentation.
Yeah.
Hate when that happens.
Yeah.
Can you share?
Share screen. The web. Wait. Let me try it again.
You had it up earlier.
Yeah, I know. I think maybe because it was in read mode. Let me see. There it is. Okay, sure. Can you see it?
Yep.
Yes.
All right, great. I put it. All right, so thank you, everyone. And I can't see myself, so hopefully you can see me. But this presentation is very timely because, as you know, the OSIRIS-Rex returned the sample from asteroid Bennu on September 24th. And so I'm going to be talking about the results of that. And there was another mission by the Japanese version of NASA, JAXA, the Hyabusa 2 spacecraft went to Ryugu. So OSIRIS-Rex is actually an acronym. The O stands for origins, where do we come from? SI is spectral interpretation, what's out there. Resource, RI, resource identification, can we use it for fuel? Security, can we prevent an impact? And regolith explorer, let's bring the samples home. OSIRIS-REX, OSIRIS-Rex. Isn't that cool? And this is the principal investigator, Dante Loretta. We'll talk about him in a bit. And then, so this is our first view of the asteroid here. This is with radar. And what's cool about radar is you get a complete rotation of the asteroid in time and you can get a shape model. And that's what this is. So the size is 510 meters. And since we don't think in meters, this is how many feet. 0.3 miles or 5 football fields. It's a spheroidal shape, a spinning top. It rotates every 4.3 hour period, and it's a near-Earth object or near-Earth asteroid. So if you look at here from the top, can you all see my
yes.
pointer
yes.
here?
Yes, we can.
All right, good. So you see Bennu here, see, comes close to the Earth. It's not the main asteroid belts out here between Mars and Jupiter. So this is actually within within the asteroid belt. So how big is Bennu? It's just a little bit taller than the Empire State Building. So it's not really that huge of an asteroid. So why was the asteroid chosen? We have over 500,000, that's 500,000 asteroids whose orbits are well known and calculated. Out of those, 7,000 are near-Earth crossing asteroids. And out of these 7,000 Earth asteroids, 192 have optimal orbits for sample return. And out of these 192, 26 have a diameter greater than 200 meters. And out of these, 5 are carbon rich. And out of these 5, Bennu is chosen. So it's kind of neat. So we're going to talk more about all this in a bit. So Osiris is actually a mythological god of Egypt. Okay, so he was the god emperor, son of the sky and earth. So this is basically Zeus to the Greeks and Jupiter to the Romans. Okay, so Osiris was to the Egyptians, Jupiter to the Romans, and Zeus to the Greeks. So OSIRIS-REx seeks to bring organic compounds back that led to the origin of life. And the original name of the asteroid was not Bennu. It was asteroid 101955 1999 RQ36. Oh my God. That's a mouthful. So the Planetary Society put out a contest to name this asteroid, and a 9-year-old, Mike Puzio, a 9-year-old, named it Bennu. And what fascinates me is a 9-year-old actually knew Egyptian mythology. I didn't know any Egyptian mythology at 9 years old. I went to Egypt and shortly after 9/11, and so I learned about Egyptian mythology then, but I had no clue at 9 years old. So that's pretty impressive. So Bennu is an Egyptian mythological bird that was born from the heart of Osiris. So everything in Bennu is named after birds. And this is like a great white, a great blue heron. And if you look here, doesn't that look like a bird? Here's the wings, the solar arrays. Here's the body. Here's the beak right here. This is the capsule that came back. And then here's the legs. And think of this as like a flamingo standing on one leg. So it does look kind of bird-like. Okay, so here's the timeline. It was selected in 2011 and then launched 2016. It arrived about 2 years later, 2018. It actually picked up the sample October 2020. It departed in 21, and it arrived September 24th, 2023, just shy of 2 months ago. So it's really recent stuff. Okay, and here's how where all the instruments are. These are called the solar panels. This is the sample return capsule right here. This separated and brought back the samples. This is the touch and go. This is the actual, that's this here that actually touched down and took the sample. And then these are all different either cameras or spectrometers for analyzing the surface of the planet. And then so this is how Bennu looks, all 4 sides of it. Here's a complete rotation you can see, and then here's it laid out flat. Notice the craters. The craters are not very deep. They're just basically pits, and that's because this is kind of what's called a rubble pile asteroid. It's very loosely held together by gravity. It's not a solid rock like granite is. Okay, if you took a hammer, you could easily it'll just shatter. So it's very, very fragile. So as the impact hit, the energy scattered more throughout, so it didn't really make a nice crater. You need a more solid surface to have a distinct crater form. And so surprise, Bennu is very rocky. This surprised scientists because it was expected to be fine-grained like a sandy beach. Why? Because of a concept called thermal inertia. So remember when you walk on a beach, right, barefooted, thermal inertia means smaller particle size, heats up quickly and cools quickly. So when the sun's shining on the beach sand, your feet feel hot because it heats up quickly. And then once the sun sets, if you're still there and walking at night, it cools very quickly too. So based on this, scientists thought that it was much finer much finer. But look at this. Once we got close enough, there were boulders the size of cars, houses, and football fields. The tallest one was a 6-story building. I mean, wow. You know, they didn't and this was made for a sandy beach. Okay, this wasn't made for something rugged like this. So the reason we were fooled is because the boulders are porous, and anything porous would have a low thermal inertia, which means it would heat up quickly and cool quickly. Plus, it was covered with regolith, which is just dirt from the asteroid. So it's covered with dirt and dust, along with being porous. So from our view, from this here, it appeared to be like a sandy beach. See, so we were fooled, but there's no going back. So it's a rubber pile asteroid, like I mentioned. It has a albedo, is just a fancy term for reflectivity. So a mirror would have a albedo of 100%, will reflect 100% of the light that strikes it. Charcoal briquette or freshly paved tar will reflect about 7%. So here it reflects only 4.5%. Okay, so it's very, very dark, very jet black, and the density is very low, 1.19 gram. Most rocks are 4 or more grams per cubic centimeter, so it's not very dense at all. And then these here, I have a slide for each, but I'll just read it out loud here. Water is present in the rocks. 2.7 micrometer band detected in the spectrum. Minerals are transformed by water into phyllosilicate, clay, and magnetite. Close match with Ci and Cm meteorites. The surface speeds up 1 second per year, 131 feet per day via the Yartowski effect, and particles were seen to be ejected. And check this out. A black hole in outburst was discovered by one of the instruments. And here it is right here. This is in the X-ray. And here's the shadow of Bennu right here. So isn't that cool? Look at that. So they actually detected a black hole in outburst on November 11th, 2019. So this is the Yarkovsky effect. So it's a real simple concept. The sun shines on something black, it absorbs the heat. And then as this asteroid rotates, it rotates pretty fast. 4 hours does the complete rotation, 4.3 hours. So as it gets to the other end, it's cold here in space, and so it's cooler. So the energy that is absorbed here is re-radiated away, and so this creates a thrust, and so that changes the orbit over time of the asteroid. See, so does that make sense? The sun heats it up, and as it rotates to the dark side here, the excess energy that was absorbed is now re-radiated away, and this kind of creates a thrust, and that moves at 1 second per year, or 131 feet per day. Okay, so conformation of water and hydrated minerals. So this is the asteroid meteorite link. So Bennu is right here. So notice it's pretty, all the meteorites in Bennu are pretty flat. And then once you hit 2.7, see, they all have a big dip, okay? And the dip is due to water, okay? And the closest match are these two, the Cm, which is Murchison right here, and Ci, which is Orgay. And then I have, I don't know if you can see it, but I'm holding up a Murchison and Orgay here, so you can see they're very, very dark.
We can see.
Huh? Can you see?
We can
them?
see.
Oh, great. Okay. So, so that's the Bennu meteorite match. It matches most closely the Ci and the Cms. Okay, and then this was very surprising. Remember, I said it has a dark albedo 4.5, but notice there were very bright white flakes here that were found on Bennu. And they took spectra of this and they found out that it was igneous pyroxene. And these bright boulders matched the spectrum from asteroid Vesta from the Dawn mission. And I have a presentation on New Dawn asteroids, Vesta and Ceres visited. Hint, hint. I may have given it, I don't remember, but I'll just give it again. So, but this is an interesting mission to the two largest asteroids in the solar system, Ceres and Vesta. But this is actually a piece of Vesta. So how did it get there? Two theories. One, Bennu may have formed in the inner asteroid belt from a larger parent body that shattered and reassembled outside the main belt. Because remember, this crosses the Earth. Or asteroid Vesta, Vestoids, pieces of it impacted Bennu in its current Earth asteroid position. So those are the two ideas. But that's an interesting find. Okay, another surprise, Bennu is active. Okay, this was discovered by Dr. Karl Hergenrother, and he's the ALPO Association of Lunar and Planetary Observers Comet director. So that's interesting. And I heard a lecture from him in the Night Sky Network, and I gave him a personal message and I said, "Are you the one that discovered the particles being injected from Bennu?" He said, "Yep, that's me." So I thought that was kind of neat. So he described from the lecture, this is what he described. He said he thought he saw a star cluster near here. See, it's all dark over here. And then he looked on Stellarium and where the position of where Bennu would be, and then those star clusters in that area, and the stars are too faint to be seen. And so Bennu, and then it was determined that Bennu is active in shedding material from its surface. And this animation here, the trajectory of all these has actually been calculated. Isn't that cool? So these are moving out in real time. And so January 19, 2019, they calculate, see it's rotating here and it shows how they're moving. That's really cool. And from that, they can determine the internal density, which isn't homogeneous. So the inner core, the equatorial bulge, and the rest of Bennu, notice they all have a different percentage of internal density, which is really, really cool. So this is the first time we've ever seen an asteroid shedding pieces of itself out into space. That's never been seen before. So proposed mechanisms, these are the three that are the most likely: meteoroid impact, okay, thermal stress fractioning. Remember, one side, due to the Yartaski effect, gets hot, and then as it rotates, it releases the energy, and then that can cause that release of energy can cause cracks and stress, and then it flies off. Think of when it snows in New England and ice forms, right? And then the ice expands and starts breaking the tar and you get a pothole. It's kind of the same idea. And pieces of the road start flaking off. See? So it's kind of the same idea. Or electrostatic levitation, which is the electrostatic forces are higher than the gravity, and so it's lifted off that way. And then the solar wind could sweep some of it too, etc. So it's kind of neat. All right, so where are we going to land? Remember, we want to take a sample of Bennu and bring it back to Earth. So 4 sites were chosen, okay? And well, one slight digression here. I think everyone knows the group Queen, right? Brian May, right here and here, he was the guitarist and one of the founding members. And what was interesting is when Queen first formed, he was working on a doctorate, PhD in astrophysics at Imperial College of London, which is ranked 6th best university in the world, okay? That's really amazing. So once Queen took off, he left, and he wrote and co-wrote a lot of the songs. He actually made his own guitar. He had his own solo career. He's one of the top 10 guitarists, inducted Rock and Roll Hall of Fame. He has a genius IQ. His net worth as of 2023 is $260 million. And then asteroid was named after him. He was knighted. But what impressed me the most is after 30 years, he actually went back in 2007 to complete his PhD. And the PhD thesis is a survey of radial velocities in the zodiacal light dust cloud. It's 256 pages. Google it, Brian May's PhD thesis. And I downloaded it and looked it over. I recognized some integrals and derivatives, and he has animations there, and he has all the codes that he had to write. And I read an astronomy magazine interview, and he said when he went back, he had a lot to catch up. He needed to learn computer coding and programming. And oh my God, I mean, if you were worth over $200 million, would you go back and get not a bachelor's, but a PhD in astrophysics to boot? I mean, that's really impressive. And right here, Roger Taylor, who's the drummer, he was going to be a dentist. He didn't go back and complete his dental degree and open up a dental practice, right? But I mean, and dentistry is more lucrative than astrophysics, but it's really, really amazing. And but what's his role to this? He co-wrote a book. Here's the primary author, Dante Loretta. If you can see the book here, Bennu in 3D, Anatomy of an Asteroid. This is $50 on Amazon, and it has really every little area here is on here. And then it has these stereoscopic glasses here, so you can see it in stereo the way he did. So Brian May was responsible for putting this together and helping determine which site to land on. So really incredible stuff. Okay, enough hero worship. Now back to the lecture. Okay, so these are the four sites, and everything has a bird theme in Bennu. Okay, so nightingale, kingfisher, osprey, and sandpiper. So these two, it ended up becoming between nightingale and osprey, and ta-da, nightingale won. That's where we took our sample, which is located right here. And then the site is as big as a few parking lots or a tennis court, surrounded by building-sized boulders. That's pretty scary because, if the thing that touches down hits a boulder, it's not going to be too good. So it contains mostly fine-grained dark material, had the highest color variation, which suggests diverse materials. And now we have a site. How do we get the samples? So here it is. And notice as it's coming, see, look at those huge boulders. But when it actually touches down, see, it touches down on a much finer area. So on October 20, 2020, that's when it happened. And the way it did, the way this worked is it touched down and it ejected pressurized nitrogen gas, which is inert. So the pressurized nitrogen gas, everything came out and then sucked it back up. So you got underneath the surface, and then it sucked up what was under the surface. So the goal was to collect 60 grams or 2 ounces of regolith, and the sample head could hold up to 4.4 pounds. So it collected so much. This was so successful that it was actually leaking out. And here you could see this black area here. That's pieces leaking out. Isn't that cool? And then this was then put into the sample, and then this dislodged and headed back to Earth. So this is the whole timeline here. And on September 24th, ta-da, it landed. And then notice, see, this is how it looked in space, nice and brown color. And then as it came through the atmosphere, it turned all black. And that was from the heating, but it was well insulated, so the material inside didn't get cooked. And meanwhile, the original spacecraft, OSIRIS-Rex, we're getting a twofer, we're getting a 2-for-1. It's going to another near-Earth crossing asteroid called Apophis. And in 2029, an extended mission, and this is known as OSIRIS-Apex now. So instead of OSIRIS-Rex, it's OSIRIS-Apex. See, AP from from Apophis, okay? And EX standing for Explorer. But what's kind of cool is that that's 6 years from now, so I'm going to be 70. So that's going to be my 70th birthday present. And another thing that's going to happen 2029 is there's another mission called Psyche that's going to a metal asteroid, Psyche. There's 3 basic types of asteroid. There's the S, the stony, the C, the carbonaceous, and the M, the metallic. And we've never been to a metallic asteroid before. How does a crater look on a metal asteroid? I mean, that's going to be something. So I'm really psyched about that. There's also another mission, the Lucy mission, which is what we were supposed to hear tonight. That's going to the Trojan asteroids, which is a group of asteroids that are within the orbit of Jupiter, and they're on its way, and that's going to arrive in 2027, and it's going to stay there for over a decade and see even more asteroids. But the thing is, it found a first one called Dinkimish that is in the inner asteroid belt. And this one was like a double asteroid. It's like so cool. They're circling around each other's center of gravity. So there's a lot of cool asteroid missions going out there. But back to Apophis. So Apophis is an S, like I mentioned, S type, which is a stony, and it most closely matches this, which is an LL ordinary chondrite. Okay. Can you see that? And then it's smaller, 370 meters. Remember, Bennu was 500 meters, and the closest approach is going to be April 13. And this is scary, man, because it's going to be closer than the geosynchronous communication satellites. It'll only be 19,600 miles above the Earth. So if you look here, the moon is out here, and Apophis is going to be right in here. The satellites are over here, the geosynchronous satellites, and it's going to be within the orbit of those satellites. That is scary stuff. And then here's a complete orbit from radar data of Apophis. See, so here we can get an idea of the shape of the asteroid. And what's even cooler for amateur astronomers, it will be so bright it should reach 3rd magnitude, which is easily visible to the naked eye. And it's going to move at a speed of 42 degrees per hour. So if you divide 42 by 60, that's 0.7 degrees per minute. And that's 1 1/4 full moon diameters in a minute. So if you have a half a degree eyepiece or more, within a minute, that thing, less than a minute, that thing's going to cross one end to the other. I mean, that is fast. And what's really cool is, for you astrophotographers out there, the angular diameter, it's not going to be a little dot like a star. It's going to be 2 arcsecond disk, which is the angular diameter of Neptune as seen from Earth. So isn't that wild? So this is something to look forward to, in my opinion. I mean, to see an asteroid that bright, moving that fast, and actually having a disk. And it shouldn't hit us. Okay, so sample return. So on October 11th, the NASA announced to the world, it was a live on YouTube and NASA TV. They opened up the inside of the and then here it's in the clean room here. They NASA scientists actually opened it up, and so what they found here, this was all weighed, and 70.3 grams, 2.48 ounces. So they were hoping to get 60, and they determined the weight that's in here by spinning the capsule around in space. And they're able to get the weight. That's how you weigh the Earth, you know, its orbit and everything else, its rotation. And so their scientists feel that there's about 250 grams down here. So that's a lot of grams, man. You'll see the Ryugu only collected 5 grams total. We got like over 300 grams. But there's a problem. As of this presentation, 2 of the 35 fasteners here, they can't unleash them. So they can't open up the rest of this. There's a big problem here. So they're still working on that. And then if you look at these here, you got this one stuck under here. That's some finer grain material. And then look at this. One is darker and one is stronger and weaker. So you can see, kind of get an idea of the rocks. And one sample here is actually now in the Smithsonian. So if you're ever in Washington, you can see an actual piece of Bennu at the Smithsonian. And then here's light microscopy. Bennu has a high amount of carbon, 4.7%, and this is higher than all the meteorites that we have on the Earth. And carbon is unique because it forms bonds with hydrogen, oxygen, nitrogen, sulfur, and phosphorus to produce biologic compounds. So CHONSP, chance. So basically CHON, these are the most common ones. And then we're looking for amino acids and nucleotide bases, which have actually been discovered in this meteorite here, the Murchison. So that's not a far stretch. And Bennu could have seeded the Earth with prebiotic organic compounds, okay? And then water in the form of hydrated clay minerals, phyllosilicate. Well, one thing about science is it uses really complicated words to say simple things. So clay that contains water, a mineral clay that contains water is a phyllosilicate. Doesn't it sound, you sound so smart when you say phyllosilicate. You're saying a simple thing, clay that contains water. That's all. And so electron microscope here, you see here water is locked in these what they call serpentine because it looks like snakes, these little fibers, so they call it serpentine. So water is locked in this crystal structure. And then here this is sulfide containing sulfur. And then down here we have magnetite, which reacts with magnetic fields and also can act as organic catalyst for organic compounds. And what's really cool is there's a new technique called X-ray computed tomography, which is similar to a CAT scan. And what it does is it looks inside a rock. You don't have to cut it open, and you could tell all the minerals in it. So this is really cool. So these red things that are glowing here are sulfide minerals. So this is an uncut piece of Bennu, and you can look inside and say, and like if you want to make a cut here and get the most, say, sulfide minerals, now you know where to cut. You can kind of cut right about here. You don't have as many here. So you know where to cut rather than in the center, see? So that kind of gives you a little information, or if you don't want to destroy the rock, you can look inside of it like an X-ray. Okay, so that's basically it for Bennu. Any questions? You can stop here for questions.
We didn't have a question, but we have a comment. And
okay.
See if Allison, do you want to say it or you want me to say it?
I just went to go find the textbook so I could show it to you.
Ah.
It's a textbook that Brian May was co-author on that we use for the online class to earn course credits with Oxford University.
Yeah.
So that's not the same one you held up, is it, Greg?
Yeah, I think so. Right here, right?
No, this is Bang.
Oh, okay. Well, he wrote some other ones too, but you know.
Yeah, this is one of them.
She had it. With Patrick
okay. Oh, cool. Okay.
That was cool.
With Sir Patrick Gregory, right?
Yeah.
Yeah.
He's no longer with us anymore, is he?
Who?
Patrick Moore.
Oh, Patrick Moore. Yeah. That's what the Caldwell objects are named after.
Chris Lincott was in on this, and he's the one that started Zooniverse.
Yeah.
Oh, yes, he did.
And his
graduate
research assistant was teaching the class at Oxford that I took.
Oh, wow.
Congressman?
That's quite a piece of history there too, isn't it, Allison? Thank
Yeah.
you for sharing.
Wow.
All right, sorry to derail you, but that came up in the
Okay,
text
no, no,
earlier,
no, no problem.
and you just decided to move on, so I couldn't get back to it.
Okay, so we'll start now with Hayabusa mission. Now, I said Hayabusa 2. Well, if there's a 2, there had to be a 1. So this is the Hayabusa 1, the original one. And this went to 25143 Ikawa. And here's how this asteroid looks like. And this was not as successful. This was supposed to collect from the surface, and it only collected 1 milligram or 2,000 particles. All right, that's like next to nothing. Okay, but I've read primary literature articles where they took a couple of particles and where they were able to do chemistry on. They confirmed water, organic matter, and amino acids from the thing, and they confirmed that this asteroid is an S type, which is LL, ordinary chondrite, which is this type of meteorite right here. Okay, so that's the original Hayabusa. And then Hayabusa 2, this is a successor, and here's the timeline for everything. And it collected the sample July 11, 2019, departed, and then arrived on Earth December 5th, 2020. So they've been here almost 3 years now, the samples, so that we've had time to thoroughly analyze them. And here's the layout of the spacecraft here. And notice the re-entry capsule is this little thing here. So it can't hold as much as the other one, as OSIRIS-Rex did, you know. So, but what was cool about this one is it had these little rovers here that actually landed on the asteroid, and they were able to take some measurements there. So that was really unique. And then all the other different optical cameras and spectra and everything. Okay, so here's Ryugu. Now, doesn't that look very similar to Bennu? I mean, look at that. It looks very, very similar. So this is also a carbonaceous type. It's a little larger, 900 meters instead of 500. So instead of 0.3 miles, it's 0.56 miles. It's also a rubble pile. It's also a near-Earth crossing asteroid. Also 4.6% albedo or reflectivity. The rotation period is a little longer, 7.6 hours as opposed to 4.3. Well, it is larger, so it's going to take longer to rotate. And spectra here, uniform on large scales, small scales shows differences here. Great variation in boulders which exhibit brecciation. Brecciation is when you get, if you can see this meteorite here, it's got 1, 2, 3, 4, 5 class. Those are pieces of rock that are, through an impact, get kind of melted together and form what's called a breccia or breccia, whichever way you want to say it. And Ryugu exhibits lower water content than Bennu. So these are the theories for the lower contact water content, heating, impact heating, or aqueous alteration. And then one of the theories of Bennu is that it actually formed in the main asteroid belt from a larger parent body, which through impact was shattered, and then these pieces came into the Earth crossing arena and then reaccumulated to form Ryugu. And then here you have the spectra showed a little redder region and a little bluer region, and toward the poles and the equator they were a little bluer. So the surface reddening is due to the solar heating, and the bluer craters is due to mass wasting. So this is one of the ideas of how Bennu could have formed, Ryugu could have formed. Another theory is that it could be an extinct comet. And there's something called comet asteroid transition objects, which, think about it, what comets are. They're a dirty snowball. They're rocky, and they have frozen gases of carbon dioxide, water, ammonia, etc. So think of dry ice as a model. Dry ice, you put it on a table, you'll never have a puddle of dry ice because it goes from a solid to a gas. And the reason it seems to go down is because it's denser than air. So it doesn't go up, it actually goes down. And you can see how it just volatilizes away. Well, the same thing happens in the comets in space. So here you have rocky debris and water ice, and then the solar wind basically just takes all this and blows it back, and so you get a plasma and a dust tail, all this stuff. But what happens is, what would happen if all this water, if all these ices were to just sublime away and just totally be gone, right? It would be indistinguishable from an asteroid. You couldn't tell that was once a comet because there's no more water ice there now, say. And then as it loses this water ice here, it would spin faster and faster, and it would give that this shape, this spinning top shape. So that's another theory of how it might have formed from a comet. And then the mission plan here. So this is what happened. The Hyabusa 2, here's where it ejected the rovers, and they dropped it on the surface of the asteroid, and they sent back some data. A third one was dropped a little bit later, and then the first asteroid sample, February 21st, 2019, and then it departed on November 2019, and then on December 5th, 2020, in Woomera, Australia, it landed, and then the Japanese took it. And here's how the samples look like. Don't they look pretty much very, very similar to Bennu, because they're both carbonaceous. They're both carbonaceous asteroids, okay? So they're the same class. So you expect them to look similar. Now this is only 1 inch across. All of these are 1 inch across. So 1 inch is 25.4 millimeters. So it makes it really easy. 1 inch is 25 equals 25, so in the metric. But in here, it's actually 21, all right? So, and then there were chambers A and C, and then all these subunits here. This is from a science article I read, and so this is how they split it all up, okay? And then here, this A, B, C, D. This is this A, B, C, and D. So they took samples from those exact containers. And then notice here, we got the same thing, 2.7 micrometer absorption line from just like you saw in Bennu, except this is the actual sample return. The 2.7 that you saw was from earlier, was from when they looked at the actual asteroid from OSIRIS-Rex. See, so this is a direct sample. So that's why the graphs are so much tighter and the peaks are much deeper and everything. But it's the same thing. And what you're actually detecting is hydroxyl and water, H2O. Think of water as H plus and OH minus. So here's H, H, O, H, two H's and an O. See? So this is how it splits, and this is the basis of the pH scale. But it dissociates very, very little, 1 times 10 to the negative 14. But so you have very, very little dissociation. But what it does is H plus and OH minus. So that's what you're detecting here, the hydroxyl part, the OH minus. And then to determine if you have carbon-hydrogen bonds, these are at 3.4 micrometers right here. So these are samples from A and B. And so the best match here is this meteorite right here. And this is a picture from my collection here, Tagish Lake. That's this one right here. And see, you can tell 0.02, calcium aluminum inclusion is that. They're rare chondrules, very few. These are chondrules here. And then notice the density is the closest here. And then all these others are much heavier. And then it shows the 3 microgram, micrometer band absorption. So this is the closest match. And then the coolest thing that was discovered is what are called amino acids. And amino acids are the building blocks of proteins in living organisms. And they have this chemical structure. And this is a little difficult if you haven't had organic chemistry, but here's the central carbon, and you have 4 different groups. So this is an amino group having a nitrogen. So this is a weak base. This is a carboxyl group, which is a weak acid, okay? This is a hydrogen, and this is an R. This is whatever other group you add here defines what the amino acid is, okay? So you can have another H, a CH3, CH2C. You can add anything to this, okay? And so that defines the amino acid. And when you have a carbon, a central carbon with 4 different groups, you have something called chirality or handedness. So you have right and left hand forms. And notice you can't fit a right-handed glove, a left hand, right hand, your right hand in a left-handed glove, notice. See, but if you go 180 degrees, your hands match, see, but you can't superimpose them. So the significance of this is living organisms on Earth use only L amino acids, the left-handed form, okay? And in space, there's no preference, so they're what are called racemic, DNL. The right equals the left, so you have 50% right-handed form, 50% L left-handed form. So these are the different amino acids that are formed. That 15 have been confirmed. Isn't that cool? So that is really incredible. And also polyaromatic hydrocarbons and nitrogen compounds. And then this is a major article here that's summed in Science, just came out February 24th, 2023. And I read this thing. And reading wasn't that difficult on this, but there's different classes here. So the gray balls are carbon, white are hydrogen, red are oxygen, and blue are nitrogen. So here you have amines, which are nitrogen containing. Here you have nitrogen containing what are called heterocycles. You have a ring system here. And then over here you have what are called PAHs, polyaromatic hydrocarbons. These are tar-like compounds. So if you drove to the presentation, you were driving on polyaromatic hydrocarbons on tar. And carboxylic acids here. Acetic acid, CH3COOH. Does anyone know acetic acid? What common household item has acetic acid in it?
It's vinegar.
Yes, very good. Vinegar. 5% acetic acid is vinegar. Yep. White or red, it doesn't matter. It's 5% acetic acid. Yep. So when you smell vinegar, you're smelling acetic acid. And there's acetic acid on asteroid Ryugu. Isn't that cool? And then amino acids, of course. And then this shows the samples, and this shows where it was collected here. So this is really, really cool. So this is the real detailed analysis that we're hoping that we will do with the Bennu samples, and then compare how much of, how many amines are in there, how many heterocycles, how many amino acids, how many carboxylic, how many polyaromatic hydrocarbons, concentration, different types, as from Ryugu to as opposed to Bennu. So there'll be a lot of comparisons with it. So this should be really cool. So that's it. That's my presentation, and here's the literature I read. But notice, here's a complete rotation of that. Don't they look very, very similar? I mean, they really, really do. See, look, the shape's very similar too. So okay, so any closing questions?
The shapes are what surprised me
Really? Why?
because of how similar they are.
Yeah, yeah.
And they seem to be different in structure. Bennu looks to be a little on the, you could probably punch your fist through it. And Ryugu
Right.
looks a little solid.
But yeah, but they're both pretty, yeah, like you said, you could put your fist through it. Right. That's what a rubber pile is. It would be very, very easy to just go like this, boom, and it would just crush it. Yeah. And actually, these meteorites here, this one, if you look carefully, little pieces are flaking off. It's that fragile, okay? See? So these carbonaceous chondrite meteorites are very, very fragile, and they come from these carbonaceous rubble pile kind of asteroids.
Kind of like the interior of my van, rubble pile.
That's good.
Thank you, Greg. It was such a good presentation last night and did not disappoint again tonight, especially
Thank you.
for having to do it a month ahead of time, but I knew it was fresh in your mind too. And Chris,
Yeah, it's fresh in my mind. So what the heck? I might as well just give it tonight. Yeah. So many.
go back and research that other one you said you've got on tap to see if we did it or not. If not, we'll talk about when we can put it in.
Oh, you mean the one on Vesta and Cirrus?
Yeah, I think
you did that one.
Yeah, I think he did, but I'm not sure. All right.
Yeah. I probably
maybe.
did, but I can do it again. What the heck?
Greg, you definitely did that one for us. It was fantastic.
Yeah.
Oh, okay.
Thanks, Robin.
Sure.
Okay.
I have CRS disease.
So
So old guy disease?
No, can't remember stuff.
Yeah.
can't remember stuff.
Thank you, Greg.
All right. Thank you very much.
Any
Thank you.
questions?
Have a good
I
night.
have another Zoom meeting I have to attend to. So take care.
You made it in
Thanks, Greg.
time.
Okay, good.
Greg, you can
How
stop
many-
sharing.
Ooh, 5140. Wow, that's good. Okay. Take care.